to integrate our equation, and I'm representing here the integration in our green control volume. The white arrows are the fluxes, and in the middle of each, you can see clearly from the median to the center. So it's you know, it's not a straight line from here to here. The conservation equation for the green area, the integration gives that. And then I ask you to remember in computational 1 course that we integrate the transient term, give us that. The mass, the quantity of material, the mass in the control volume, time step, recognize here that we are using a first order backward in time. It's clear here. And then remember the left side of Navier-Stokes equation. Derivative of the rho times phi. Phi now for now is the one component of the momentum conservation. Ui means it can be U, can be V, can be W. At the point P here. This is one term of the left side of Navier-Stokes equation. Then the other equations, derivative of in relation to x, the rho U phi, so is this all this. Summations in the integration points, calculating this mass flow. This is mass flow times phi. Phi is the component of the velocity for others. Then there is, I'm always repeating, remember the Navier-Stokes equation is equal to pressure gradient. It's here, pressure gradient. The PdX in the U conservation equation, the Pdy in V, the PdX and W. How do I represent that? It's Pi, which means if I'm in the U conservation equations, this P in U will be P00, because it may sound strange here. So this is pressure scalar N, but pressure is a scalar. And to do this calculation, need to be a vector here and a vector there. N, the normal, is a vector. Pressure, I can write it here. It's P00 for the U conservation, for the conservation equation for the X component of the momentum. For the Y component of the momentum, the vector is so it's a scalar pressure appears here. And then there is the diffusion here. All the derivatives of diffusion terms. I'm writing also. Tau is a tensor, has 9 components. But for each conservation equation, for U, for V, for W, for X component, Y component, and W component, zeta component of the momentum equation, I have, here's the 9 components. But when I'm using Ui is equal to U, this is the tau for U, the diffusion. So it's a vector here. When I'm in the second equation for Y, is a vector normal to scalar, to the normal. And our source term, which is linearized in this way, which is the best we can do. SP times U plus SC, which is constant. It's a constant. So what we have to do now is to make the calculations. Here, what we have to do here, to enter with our interpolation functions. So it's upwind, the central differential, a second order, everything is the same. We have to enter there. We want to see for the element base that we have some special ways to do this, to input the interpolation function there. This How do I calculate? Pressure is here in the center. But I need everything here in the integration points. Sometimes you find a PI and IP. So this ponto de integração in Portuguese, so, but the integration point, sometimes they are mixed up. No? But PI is equal to IP. Those you can do using the shape functions because they are diffusion is elliptic, and shape functions, when you use the shape functions to do some kind of interpolation, you are doing some central difference because the shape functions are linear, bilinear, trilinear in 3D, but it's like some kind of a central differencing when you use the shape function. But pressure and diffusion, you can do that because they are elliptic terms. This one is advection, is a advective term. So you cannot do central differentiation there. You cannot use the shape function. It will be too easy. If you are in the integration point here, you want to find the function in the integration point, we're using these 3 points, using shape functions. Of course, it's easy, but doesn't work. Doesn't work because doing that you are using a central differential scheme, and then we know the central differential scheme gives you negative coefficients, and this gives you oscillations in your solution, numerical oscillations in your solution. So that one is a special topic we already discussed. We discuss again in the context of element base, and these terms can be calculated using shape functions. I'm just doing some because the most known software which uses element base is the CFX, ANSYS CFX. What I'm trying to do here, just for the people who are familiar with the ANSYS CFX manual or something like that, I'm just correlating here the equations that you have in the ANSYS CFX. Again, remember Navier-Stokes equation and look at this. This is V times rho. Rho times V is mass. It's mass. Here is using U, big capital U. I'm using the small u. So this is the same term as here. This one is the summation, every integration point with the same as there is the m dot flow rate, mass flow rate. Here, rho V scalar n ds. This is m dot. This is m dot too. Is flow rate times u times u. Pressure gradient. We are going to see this convention. It's nice to have this convention to write the equations. This is the same. P delta the n. This is not the normal. It's some kind of convention I'm going to show later. It's pressure here, and this is the diffusion. The diffusion. And this is the source. I'm writing in that manner. What I want you to stress one important thing. CFX is a code. It's a numerical algorithm, which is a numerical method. It's a numerical scheme, which uses only coupled or simultaneous solutions of U, V, W, and P. And I think I already went through that, talking about that, but here's the reason now. Because sometimes you have viscosity constant problems, constant density, rho constant. Then, if you do the simplification, this term disappears. This term disappears. Remember that when I have such simplifications I will put just the one term here. We have the dx, the you have this, the derivative here, the coefficient, only one term, the u dx. And here both are kept, both terms. This one would be dropped out if rho is constant and mi is constant. If you remember from the convection course, you can join and see that the mass conservation appears and then the terms drop. But here in the CFX, those terms are kept on the equation. So there is no plus dv dx, which is the second part which cancels when you put the tensor there. And why is that? Because then you keep all the variables in the equation. Because one of these terms here is like that. Another term would be I didn't put the viscosity here. It doesn't matter. I'm not going to I'm going to show that this term, when mi is constant and then you change the derivative, d of dy, the dv dx can be written d of dx, the dv dy. But then d of dx and du dx, I can put inside this and this cancel with that. And then we don't show this. Sometimes when rho and mi is constant, is the normal way to write the equation. But it's better to leave like that, because then this is an equation for u component, x component. V is there. V is there. Because what is preferable when you have a simultaneous solution is to have u, v, w, and p. You want numbers here, numbers here, numbers here, numbers here. Numbers which multiplies u, numbers which multiplies v, numbers w. You don't want disappear in the equation for u, disappear in the v. So, and if you drop this when rho and mi are constant, there is no v in the equation, there is no w in the equation, just u. And then it will be zeros in this equation. So it's written like that, and the way I'm doing, I'm writing like that, such that in the equation for u, there is v, there is w. This term would cancel with this one and with that one. This one would cancel with this one, that one, that one. But they are kept there in order to keep all variables appearing in all equations. Then your simultaneous matrix does not show zeros. Then it's better for the solution of the equation. For a general scalar, is the same. For a general scalar, is m phi minus first order, m dot flow rate times phi, and the same diffusion terms. See, here is this mu effective. those equations are already prepared for turbulent flows. That's why it's viscosity, effective viscosity. Viscosity prepared for turbulent flow. So the equation doesn't change. The only thing we change is how to find the effective diffusion coefficient, which will be some laminar coefficients plus some turbulent coefficient. And that is the question, how to find the turbulent coefficient, which will be added to the laminar coefficient, which is molecular coefficient, such that you have the effective change, transfer of momentum, which is this. We could put there also, you know, here, to put the me effective is the same, you know. Now comes a very important part, which is a general interpolation function for phi, which is the advection term, how we treat the advection term. This is the key question in all numerical schemes. That's what gives to the software stability, if it's good, you know, if it's very well done, the algorithm gives for you stability, at some time avoiding smearing of gradients, and sometime avoiding overshoots and undershoots on your solution. If your solution ranges from 0 to 1, if your solution ranges from 0 to 1, you cannot have values which is 1.1 or minus 0.2. You cannot have that. If your solution is bounded in 1 and 0, your solution cannot have overshoots and undershoots. This is not allowed. So, and it's not easy, really not easy to have an algorithm which gives you stability, no numerical diffusion, and no numerical oscillation, which is undershoots, overshoots. The only way to do that would be to have, we talked about that already, very, very, very fine grids. Then the problem solved. But you cannot use very, 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 very fine grids. Then you have to, you know, to live with this problem. And this is one possibility, to have an interpolation function for phi, where you say that what we need to do is remember the equation. We need phi at the integration points. So the phi at the integration point can be written as an upstream phi plus how phi changes along the streamline, first order, first derivative, second derivative, is expansion that you can do here. And then you can now find ways. Because if you put everything here to 0, this is 0, and this is 0, you are just doing a pure upwind, right? You are saying that the phi, the integration point, is the phi upstream. The problem is not solved, because the key question also is to know who is the phi upstream. How do I choose the phi upstream? We're going to discuss that. But if I do that, 0, this is a pure upwind scheme. Let's increase the order of this upstream scheme, pure upstream scheme, introducing this term. Let's put that, drop that term, let's keep this one. Then we have to find, if I have some way of calculating this phi ds, S is the streamline there. If I have some way to calculate that, I'm introduce some, the literature calls anti-diffusive flux to compensate the strong numerical diffusion that you are going to have if it's upstream pure upstream. Then, pay attention, if I drop everything here, this is first order, this is pure upwind, numerical diffusion is in large amount is present. I want to eliminate a little bit of this numerical diffusion. What should I do? Is to put some higher order terms, and this will do the job. To add some, since this adds some order on that, reducing the numerical diffusion is equivalent to say I'm introduce some anti-diffusion, because pure upstream introduces a lot of diffusion. I'm to introduce some anti-diffusion in order to minimize this problem with numerical diffusion. Then how can I calculate that? Now, remember again the conservation equation. I have the left-hand side of the conservation equation. I have d over dx, the density times velocity times phi, plus d over the y derivative, and then I put everything in the u, these three derivatives, x and y and z, I put in a derivative along s. And the velocities, which are u, v, and w in three axes, I'm using the velocity along x. So this is approximately writing my conservation equations along s with a velocity v along s, which is, I have the three components, u, v, and w. And the right-hand side is diffusion, is pressure, source terms, even transient terms are all there. So then I can put that there. So the phi dx is determined according to the physics of the problem. These schemes, however, does not guarantee the positiveness of the coefficients. Then mass-weighted schemes are required. Then let's divide this topic in two main questions. The first main question is, how can I add to my upstream scheme some anti-diffusive fluxes such that I minimize the numerical diffusion? This is done introducing this term, and this term comes from the physics of the problem, but because it is extracted from the partial differential equation that you are solving. This is one question. The second question, doing that doesn't mean that your scheme will generate positive coefficients. In order to generate positive coefficients, the key question is, who is phi upstream? That's the key question. Because I can have everything nice here, but if I don't have the right way to calculate the phi upstream, and then I can introduce negative coefficients. And keep in mind, negative coefficients, they are resulted from higher order schemes. Upwind schemes does not generate negative coefficients. Let me explain this a little bit here. Let's put some one-dimensional problem here. P, W, E. If it's 1D, My integration point is small w, small double v, w. If I do that, there is no negative coefficients. The negative coefficients appears when I try to put the point E in the algorithm for that. If this is only function of that, but if it's function of that too, or other, if I do that, I may introduce negative coefficients. This is the concept which I already explained in computational 1, is the concept of donor cell. Is the concept of donor cell. Is the concept of thinking who is influencing my downstream point. Is just from upwind, or the influence comes also from downstream. We know that if it's a advection, the influence doesn't come from downstream. The influence comes from upstream. That's why upwind scheme. So the donor cell who gives the information is the upstream. And then in this case, you will have no negative coefficients. If you try to do a central differencing scheme for this point, you know, the point P will be involved, right? If you try a central differencing. Telling us that the value here will be dependent of this value, and a negative coefficient appears. So in order to have positive coefficients, the concept of a donor cell, what cells, what points really is influencing the value in the downstream position. This is the concept of donor cell. And this is why this is important, because this is the donor cell. We are saying that the phi in the integration point which I am interested depends on what is informed upstream plus what the physics changes from upstream to the integration point. And then that's what is here. But then we solve the first part, having the equation to do that. The physics is there in the equation. We need to know now to apply the concept of donor cell, because then the coefficients will be positive. But who is the donor cell? Is a matter which is not so easy to visualize, or has to be some physical. And the physics behind this is to have what we call the mass-weighted schemes. So are the weighted, which are weighted by the mass which offers the information to the integration point. And then I draw here an element, 1, 2, 3, 4. This is the phi at integration point 1. See, this is the element 1, 2, 3, 4 integration points. The element. I want to calculate the value of phi in this position. Why? Because I'm building my matrix for my element. I want to calculate the flux in the 4 integration points. Let's consider I'm focused on this one. So phi at integration point 1. Then you see you are going to recognize the streamline. Let's say that the streamline is this one. Then you could say that your phi upstream is here. How do you find this phi upstream here? You could say this, I could do some average with this point and this point put here. and say, then use this point average with this one and calculate here. This will give that one. Would involve phi 2, phi 3 nodal points, and will involve also an integration point here also. This is one possibility, but this does not doesn't guarantees that the coefficients will be positive, because it was just an average. There is no much physics on that. So just an average of the upstream values in order to find your upstream. If the streamline was like that, you could do an average between this phi and that phi, integration points, IP and 4 here. If you go through to the 4 integration points, you can realize that I may have all my 4 phi's at the integration points as function of nodal points and as a function of other integration points, which are also I'm trying to find. So there will be a little matrix 4 by 4 to be solved. Can you see that? It's going to be a matrix, because if I do that, the phi upstream here, the phi in P1 would be function of all this, that, and also function of upstream. So it will be a 4 by 4 matrix in 2D and 12 by 12 matrix in 3D. If you say, I'm not going to put my phi upstream as functions of others integration points, only from the nodal points, there will be some averaging also. There will not be no matrix, but you are prone to have negative coefficients too. So the determination of phi upstream is not a matter of only do some average. It's a matter of using mass-weighted schemes. I'm just trying to put some slides saying finding the upstream point. I already stated firmly that it's not a matter of doing some average over the upstream points in order to find the phi upstream, which gives the information to the integration point which I want. It's a matter of using, I'm repeating, the concept of donor cell. Who does the information? One way to do this is just to say, again, pure upwind scheme. If I have, here's my element, if I have a flow like that, I'm interested in calculating the flux here. I'm saying that the upstream is the number one. Phi upstream is the phi at point P equal to 1. This will not give me the right coefficients, positive coefficient. If it's like that, the streamline, I will gonna say that applying the upstream, pure upstream, it's saying that the upstream now is the 4, saying that what is influencing this point is that one, but if the flow comes from this position, this point is also. And then you could do a summation of these two and have some here, but doesn't guarantee you positive coefficients. If you do pure upstream, you are guaranteed positive coefficients, but you are carrying also some numerical diffusion.